Hey there, STEM Chemistry. This is Ms. Ruark. This is Vodcast 5.1, where we're going to talk about chemical reactions. A lot of this should be review, so we're going to go quick. Remember, you can always pause, rewind, and rewatch if you need to. All right, so describing chemical reactions. They happen all the time. They happen everywhere around you. Every single time you turn around, there's a chemical reaction happening. Okay, so what are some examples of those? Well, yeah, I'm not trying to get creepy on you, I promise. I'm just breathing. Breathing is a chemical reaction, right? You're taking in oxygen, you're giving out carbon dioxide. That's a chemical reaction. What's something else that happens every day? Well, you gotta eat, don't you? Digestion, that's another chemical reaction that's happening inside of your body, right? It's starting to get colder. So what if you guys decided that you wanted to burn a fire? So if you're going to burn wood, that's another chemical reaction that's happening all the time, right? All the time. Let's see, what are some other ones? Gosh, anything. If you have a banana that's sitting on your counter, that banana, once it turns brown, if it's ripening, that's another chemical reaction that's happening right in front of you. We could do this for days, but we're not going to worry about it. You guys get the point. All right, so what are points or some signs that a chemical reaction has happened? Well, there's 5 of them that would show us that a chemical reaction has happened, and the first one is a change in color. Okay, now what do we mean by change in color? We'll see here we've got a clear colorless solid liquid that's being poured into another clear colorless liquid. If you take two things that are clear and colorless and you put them together and they make this yellow stuff here, that's a color change because it wasn't expected. Now, if you take a blue and you take a yellow and you put them together and you make green, that's kind of expected. That's not what we mean by color change. All right, what about this stuff that's forming in the bottom here? That's a solid. So formation of a solid. And now we also call that solid, let's use correct terminology, we call it a precipitate. All right, well, what if you were to take an Alka-Seltzer thing and drop it into water and it makes bubbles? Oh, formation of a gas, that's another sign. Okay, well, what if we were to take two things, mix them together, and they started to feel warm to the touch? Okay, so a change in energy, an energy change. If we were to feel cooler or warmer to the touch, if it was to give off heat or light or take in heat or light, that would be an energy change. And then the last one, oh, sad face. And then the last one would be a change in pH, and that would also indicate that a chemical reaction has happened. Okay, so chemical equations. Like I said, we're going to go through this kind of quick because, well, you guys already know this. So, representation of a chemical reaction. Let's say that we have methane gas, and that's going to be reacting with oxygen, combusting with oxygen to form carbon dioxide and water. Sounds good. All right, so our reactants, I'm not going to write these, you can. These are our reactants, the ones on this side. They're the things that are coming together. My products are going to be the things on the other side of the arrow. Those are the things that you're making. And that arrow tells us it's yielding. Now, that's not the yielding when you're stopping and slowing down oncoming traffic. This means to make, to form, to produce. All right. There's different ways you can represent this. You can do a chemical sentence. All right, so let's say that we have that same CH4 plus O2 gives us H2O plus CO2. Okay, so the chemical sentence would be if you actually take those things, CH4 is methane gas, plus oxygen, arrow, water, plus carbon dioxide. So all you're doing is you're taking the formulas and you're changing them into words. Everything else stays the same, the pluses, the arrows, everything. Okay, remember, you can pause if you need to. All right, so a word equation, the same equation if you have CH4 plus O2 arrow CO2 plus H2O. All right, so this is actually taking it and making it into more of an English class because we would say methane gas reacts with oxygen or gaseous oxygen to form or to produce or to make carbon dioxide gas and water vapor. Okay, water vapor is just another fancy way of saying gaseous water, right? Okay. All right, so here's an example. We have iron plus oxygen gives us iron Fe2O3. What are the products? Our products are going to be Fe2O3. Oh, sad face. Okay, Fe2O3. My reactants are Fe and oxygen. And then the chemical sentence, I'm going to let you write those and then we can check them when you come in. I'm sure you've got this, but I don't want to waste any time doing it if I don't have to. Okay, so pause it and write it. All right, so symbols that we need to know when we're doing our chemical equations. S, if you see S after something that has parentheses around it, it's saying that this is a solid. If you see L after something, it's a liquid. If you see AQ after something, it's an aqueous solution, which means that it has been dissolved in water. Aqueous, aqua, water. Okay. G means that it is a gas, or it's a gaseous state. All right, those are easy. Let's get to some more. What if we had something that's used to separate two reactants or products? That would be a plus sign. Okay, so if you have more than one reactant or more than one product, you have to have a plus sign. Something that separates the reactants from the products would be the arrow or the yields. If it's a reversible reaction, you will have two arrows. Don't do a double-headed arrow. It would be two arrows, one going in one direction, one going in the other. If one of the reactions is favored more than the other, the arrow that's not favored would be small. We'll get into that in equilibrium. All right. If heat has been used in a reaction, we put a triangle, which stands for heat. And if it's a catalyst, if any catalyst has been added to it, we would put the catalyst over top of the arrow. Or you could put it under the arrow. It doesn't matter. Okay, and that shows that the water was the catalyst that made the reaction happen. All right, so what is a catalyst? Well, a catalyst is a substance that's going to speed up a chemical reaction, but it's not going to be used in the reaction. Okay, so for example, here we have iron plus oxygen, and if we take iron and oxygen and we add water vapor to it, it'll speed up this process and form iron 3 oxide. Guess what? That's rust. Yes, that's what happens when you rust, when your car rusts. All right, so what's the catalyst in this reaction? The catalyst was the water. What phase is each of the substances in? So iron is in the solid phase because it has an S after it. Oxygen has a G after it, so it's a gas. And then the S after the iron 3 oxide says that it is also a solid. Okay, I know I'm going fast, but I hope that this is, you're getting this. You're smart. You get this. Okay, writing chemical equations. So here, we are going to just take a word equation and write a chemical equation from it. Okay, so make sure that you have your reactants on one side, your arrow, and then your products on the other side. So here we have solid sodium oxide. So solid is going to be S, and sodium oxide, sodium is Na with a positive 1, and oxide is O with a negative 2. We cross those and we end up with Na2O. Reacts with, that tells us we need a plus, water. Oh, that one's easy. H2O. And if it's water at room temperature, that must mean it's a liquid. All right, to form, arrow, aqueous, AQ, that one's the fun one. Sodium hydroxide. Sodium is Na with a positive 1 charge. Hydroxide, OH with a negative 1, and those will cross down and cancel, so we end up with NaOH. So our chemical equation will be Na2OS plus H2OL, arrow, NaOH, AQ. That's not bad, is it? Not at all. You guys got this. Okay. All right, so once we get down the writing equations, then we need to balance equations. And we use the law of conservation of matter, or the law of conservation of mass, to help us balance equations, because matter cannot be created or destroyed in a process. It can change its state, it can change forms, but it cannot be created or destroyed. When we balance equations, both sides of the equations must have the same number of atoms for each element. Right? And how do we do that? Well, we do that only, but we can only the coefficient can be adjusted. Okay, we can't adjust anything else. You can never change the subscript. Okay, everybody loves to change the sub. You can't change the subscript. It's what helps to identify. You can't change that, but you can change anything that goes in the front. Okay, so here are some examples here. If I've got one carbon on this side and one carbon on this side, we're good. If I've got 2 and 2, it's already balanced. Yay! On this one, I have 1 iron and 1 iron. Here I have 8 sulfurs. I only have 1 sulfur, so we would have to change it in front. But guess what? That also changes my irons, so I'd have to come back and change that one too. We're going to practice this. Okay, one thing, don't forget, Brinkelhoff, diatomic, which means if they're by themselves, there has to be 2 of them. Okay, and you can change the quantity of something, but you can't change the identity of something, so don't change subscripts, add anything else. You can only change the big number. All right. Oh, and that's it. Oh, that's awesome. Okay, so you guys have lots of practice coming up. It says if you're not part of the solution, you're part of the precipitate. That was great. All right, and I want you to do the practice, the balancing equations practice, and we're going to go over it in class to make sure you guys are where you're supposed to be. All right, guys, I'll see you later.